Hello everyone, welcome back to the AI Academy. It's great to see you all again as we continue our journey into the world of ethical hacking. In our last lecture, we laid the groundwork for understanding IP networking, focusing on IPv4 addressing, routing, and subnetting. Today, we'll continue to the realm of IPv6 to understand how it addresses modern networking challenges. Let's take a quick recap of what we discussed in the last lecture. We learned how IPv4 addresses uniquely identify devices on a network, allowing seamless communication. We explored the concept of fragmentation, which allows large packets to traverse networks with smaller maximum transmission units (MTU). We examined how subnetting helps optimize IP address allocation for networks of different sizes. In today's lecture, we will be learning the understanding IPv6 addressing. We'll discuss the structure and types of IPv6 addresses and how they differ from IPv4. We'll explore how IPv6 improves upon IPv4 in terms of routing efficiency and built-in security features like IPsec. We'll dive into techniques like dual-stack implementation and tunneling, which help during the migration from IPv4 to IPv6. By the end of this lecture, you'll have a solid understanding of why IPv6 is critical for the future of networking and how it enhances both performance and security. So, let's first discuss why we needed IPv6. The challenges with IPv4 are like address exhaustion and its impact. The IPv4 uses 32-bit addressing, which provides a theoretical limit of approximately 4.3 billion unique IP addresses. While this number may seem large, several factors have contributed to IPv4 address exhaustion, such as explosive growth of internet-connected devices, the rapid proliferation of personal computers, smartphones, IoT devices, and industrial sensors has far outpaced the number of available IPv4 addresses. The inefficient address allocation. Early allocation practices assigned large blocks of IPv4 addresses to organizations, often more than needed. For example, the Class A and B address schemes in IPv4 led to significant underutilization. The rise of always-on connections. With the adoption of broadband, devices remain connected to the Internet 24/7, tying up IP addresses for longer periods. Geographical disparities. Some regions, especially developing areas, face challenges acquiring sufficient IPv4 addresses due to earlier allocations favoring developed countries. The impact of address exhaustion are like increased reliance on network address translation. The NAT allows multiple devices on a local network to share a single public IPv4 address. While this alleviates address scarcity, it introduces challenges such as reduced end-to-end connectivity, complications with protocols requiring direct IP address mappings, such as VoIP, peer-to-peer applications. NAT adds complexity and can create security vulnerabilities by obscuring the true source of traffic, like the increased costs. The organizations face higher costs for obtaining IPv4 public addresses from secondary markets. ISPs often resort to carrier-grade NAT, CG-NAT, adding infrastructure expenses. And the innovation bottleneck. The scarcity of addresses limits the deployment of new services, especially those requiring extensive IP allocation, such as IoT or smart city applications. Another issue was security limitations in IPv4 compared to IPv6. The IPv4 was developed in the 1980s, primarily for research purposes, with limited attention to security. As the Internet evolved, the security shortcomings of IPv4 became apparent. For example, no built-in encryption or authentication. IPv4 does not natively support encryption or authentication, making it reliant on external protocols like SSL/TLS and VPNs to secure communications. This adds complexity to securing IPv4-based communications. Susceptibility to spoofing. The IPv4 lacks mechanisms to verify the authenticity of source IP addresses, making networks vulnerable to IP spoofing attacks. The weaknesses in address resolution protocol are like the IPv4 networks use ARP to map IP addresses to MAC addresses. ARP spoofing can be exploited to reroute or intercept traffic. The reliance on additional protocols for security. The IPv4 depends on protocols like IPsec for secure communications, but their implementation is optional. This results in inconsistent adoption across networks. Let's understand how IPv6 addresses handle these challenges. First one is the abundant address space. The IPv6 uses 128-bit addressing, providing approximately 3.4 by 10 to the power of 38 unique addresses. This ensures enough addresses for the foreseeable future and eliminates the need for NAT, enabling end-to-end connectivity. Built-in security. The IPv6 was designed with integrated IPsec support, offering optional encryption and authentication for network traffic. This standardization simplifies secure communications across devices. Enhanced addressing mechanisms. The IPv6 includes features like Stateless Address Autoconfiguration, which simplifies device configuration and reduces administrative overhead. By addressing these critical limitations, IPv6 not only resolves the issues of address scarcity and security but also lays the groundwork for a more scalable and secure Internet. So, the IPv6 protocol is designed with scalability, efficiency, and security in mind. Ready to dive deeper? Let's explore how IPv6 addresses work. Now that we've covered the basics of IPv6, let's talk about how devices get their addresses in an IPv6 network. One of the coolest things about IPv6 is that it makes address configuration a lot more flexible and intelligent compared to IPv4. The Stateless Address Autoconfiguration, SLAAC and the DHCPv6, are the two primary methods. What is SLAAC? The SLAAC allows devices to configure their own IP addresses without the need for a central server like DHCP. It's like devices saying, "I've got this covered," and figuring out their own unique addresses based on information provided by the network. Here's how it works. Let's understand how SLAAC works. Step 1. The router advertisement. Routers on the network periodically send router advertisement messages using the Neighbor Discovery Protocol, NDP. These RA messages contain the necessary prefix information for devices to generate their addresses. Step 2. Generating the address. The device combines the network prefix, from the RA, with its own interface identifier, typically derived from its MAC address. This results in a globally unique IPv6 address. Step 3. Verification. Before using the new address, the device performs a duplicate address detection (DAD) process to ensure no other device on the network is using the same address. The key benefits of SLAAC are: no need for a server. SLAAC eliminates the dependency on a DHCP server, reducing administrative overhead. Ease of deployment. Great for networks where simplicity and scalability are priorities, like IoT environments. Let's now discuss about DHCPv6 equivalent to the DHCP in IPv4, but with enhancements tailored to IPv6. It can operate in two modes, stateful and stateless. Stateful DHCPv6. In stateful DHCPv6, the server is fully in charge of assigning IPv6 addresses to devices, just like in IPv4. Here's how it works. The process includes following steps. Step 1. Devices send a solicit message to find a DHCP server. Step 2. The server responds with an advertise message, offering an address. Step 3. The device then sends a request for the offered address, and the server confirms it with a reply. What the server does. It tracks which devices have which IP addresses. It can also provide additional configuration info like DNS server addresses. Best use case of having DHCP server is the environments where administrators need tight control over IP address assignments, such as enterprise networks. Stateless DHCPv6. The stateless DHCPv6 is a hybrid approach that complements SLAAC. Here's how it works. The process includes steps like Devices use SLAAC to generate their IP addresses. And the stateless DHCPv6 provides additional configuration details, like DNS server addresses or domain names, which SLAAC doesn't handle. The key difference between the stateful and stateless DHCP is that the DHCP server doesn't manage or track the IP addresses, it's only used to supply extra information. The best use case may be the networks that want the simplicity of SLAAC for address configuration but need more detailed network settings provided by DHCP. Let's now talk about SLAAC and DHCPv6, two tools for configuring IPv6 addresses. They're like different tools in a toolbox, and knowing when to use each one can make all the difference. So, let's break it down. Address assignment. First, how do devices get their IP addresses? With SLAAC, the devices handle it themselves. They figure out their own IPs, pretty independent, right? Stateful DHCPv6, though, says, nope, I'm in charge. The server assigns and manages the IPs, just like in the IPv4 world. Then we have stateless DHCPv6, a little hybrid. Devices still configure their own addresses, but the server steps in to give some extra details. Do you need a DHCP server? Here's where things get interesting. SLAAC? Nope, it doesn't need a DHCP server at all. It's self-sufficient. Both stateful DHCPv6 and stateless DHCPv6, on the other hand, rely on a DHCP server to do their job. Extra configuration info. Okay, so what about those additional settings like DNS servers? SLAAC is pretty basic. It gives you the gateway info, and that's about it. But with stateful and stateless DHCPv6, you get more. These can provide details like DNS settings or domain names. Handy, right? Control over IP assignments. Now, let's talk about control. How much say do you have in which device gets which address? SLAAC? Not much. The devices do their own thing. Stateful DHCPv6. Full control. The server tracks and manages everything. And stateless DHCPv6? It's like SLAAC, low control. The server only helps out with extra details, not the addresses themselves. Best use cases. So, when do you use each one? SLAAC is perfect for simple setups, like IoT devices or home networks, where you just want it to work without much hassle. Stateful DHCPv6 is ideal for enterprise environments where you need to tightly manage and track all the IPs. Stateless DHCPv6. That's your go-to for hybrid scenarios, when you like SLAAC simplicity but need a little extra from DHCP. How does it matter in ethical hacking? For ethical hackers, understanding how IPv6 addresses are assigned is crucial because it helps to identify potential vulnerabilities in configuration processes. Know where to look for attack vectors, like unprotected RA messages in SLAAC or misconfigured DHCPv6 servers. Simulate real-world scenarios, such as spoofing RA messages to redirect traffic in SLAAC environments. So, whether it's the simplicity of SLAAC or the control of DHCPv6, IPv6 provides flexible tools to meet the needs of modern networks. Let's now discuss about the IPv6 header structure. It is the foundation of IPv6 packet processing. It's designed to be simpler and more efficient compared to IPv4, addressing limitations in the older protocol. Let's break it down step by step. Let's start with a side-by-side comparison of the IPv4 versus IPv6 headers. Think of this as the before and after shot of networking. Header size. In IPv4, the header size is variable, ranging from 20 to 60 bytes, depending on the options used. While with IPv6, they streamline things, a fixed 40 bytes. No more guessing games, and it's easier to process. The address length. In IPv4 uses 32-bit addresses. Back when the internet was just starting, that seemed like plenty. But IPv6 takes it to a whole new level with 128-bit addresses. That's a massive space for devices, no more worrying about running out of IPs. The options field. The IPv4 includes options as part of the header, but that adds complexity. While the IPv6 moves options to extension headers, keeping the main header clean and efficient. The checksum. The IPv4 includes a checksum, but it adds processing overhead since it needs to be recalculated at every hop. While the IPv6 says, let's skip it. The checksum is gone, improving efficiency and leaving error checking to higher layers. The fragmentation. In IPv4, routers can fragment packets, which can slow things down. While the IPv6 shifts this responsibility to the end hosts. They handle fragmentation, making routing faster and more straightforward. The security. The IPv4 doesn't have built-in security mechanisms, you must configure them on separately. While the IPv6 comes with native support for IPsec, making secure communication a standard feature. So, there you have it, the IPv6 header isn't just an upgrade, it's a redesign for the modern internet. It's efficient, scalable, and better equipped to handle the needs of today's connected world. The key simplifications in IPv6 are like the fixed header size. The IPv6 header is always 40 bytes, simplifying processing for routers and hosts. In IPv4, options could extend the header size, causing variability and processing delays. No header checksum. The IPv4 headers include a checksum that routers must recalculate at every hop. IPv6 eliminates this to improve performance, relying instead on checksums in transport layer protocols like TCP or UDP. The extension headers. IPv4 embeds optional fields in the main header, while IPv6 moves them to separate extension headers. This modular approach reduces overhead for common packets. The version, 4 bits. It identifies the version of IP being used, 6 for IPv6. And ensures compatibility and proper handling by routers and hosts. The traffic class, 8 bits. Supports differentiated services by marking packets for priority handling. For example, real-time traffic like voice calls can be prioritized over email. Flow label, 20 bits. A unique identifier for a flow of packets, such as video or gaming traffic. It enables routers to process flows efficiently, reducing latency. Payload length, 16 bits. Indicates the size of the data portion of the packet, excluding the header. Supports payloads of up to 65,535 bytes, with larger payloads handled by extension mechanisms. Next header, 8 bits. It specifies the type of header that follows the IPv6 header. Transport layer headers like TCP, value 6, or UDP, value 17. Extension headers like hop-by-hop options or fragmentation. Like the IPv4 protocol field but more versatile due to extension headers. Hop limit, 8 bits. It prevents packets from endlessly circulating in the network. Decrement by 1 at each hop, if it reaches 0, the packet is discarded. Source and destination addresses, 128 bits each. Provide the unique IPv6 addresses of the sender and receiver. Enable IPv6's vastly expanded address space, accommodating trillions of devices. Why these changes matter? First is efficiency. The streamlined design reduces overhead, speeding up processing at each hop. Scalability. 128-bit addresses ensure IPv6 can handle global demand for IP addresses. Flexibility. Modular extension headers allow IPv6 to adapt to new technologies and needs, without overcomplicating the base header. The IPv6 header structure is a perfect example of thoughtful engineering, simplifying network management, improving performance, and future-proofing the Internet. Next, let's explore IPv6 address configuration to see how devices use this protocol in action. Let's first discuss about Neighbor Discovery Protocol, NDP. The Neighbor Discovery Protocol is a crucial component of IPv6 that replaces and enhances several functions of IPv4 protocols like ARP, ICMP router discovery, and others. Let's explore its role and vulnerabilities, as well as strategies to mitigate potential risks. The NDP operates using ICMPv6 messages and is responsible for essential networking functions like router discovery, address resolution, and prefix discovery. The router discovery helps devices identify the routers on the local network that can forward traffic to other networks. How it works. The routers periodically send router advertisement messages to inform devices about their presence and configuration settings. The devices can also send router solicitation messages to actively query for routers when they need immediate configuration. The key benefits are: automatic configuration without manual setup. It enables devices to dynamically select the best router for traffic forwarding. Let's now discuss about the prefix discovery. It allows devices to discover the network prefixes associated with the local link. This is essential for generating their own IPv6 addresses using SLAAC. How it works. The RA messages from routers include the network prefix information. And the devices use this prefix to construct a complete IPv6 address by appending their interface identifier. The key benefits are like: it simplifies IP address assignment, especially in dynamic environments, and eliminates the need for centralized DHCP servers in many cases. Let us now discuss about the address resolution in IPv6. It maps IPv6 addresses to corresponding link layer addresses, such as MAC addresses, similar to ARP in IPv4. How it works. When a device needs to send a packet to another device on the same link, it sends a neighbor solicitation message asking, "Who owns this IPv6 address?" The owner replies with a neighbor advertisement message containing its MAC address. The key benefits of ARP in IPv6 are that it is more efficient than ARP, as NDP uses ICMPv6 messages instead of broadcasting. Prevents unnecessary network congestion caused by broadcast ARP traffic. Let's now discuss about vulnerabilities in NDP and its mitigation techniques. While NDP is a significant improvement over its IPv4 counterparts, it's not immune to vulnerabilities. Here are some common threats and ways to address them. The first one is spoofing attacks, in which the attackers can send malicious NDP messages, such as fake RA spoofing or NA spoofing, to redirect traffic or impersonate other devices. For example, an attacker sends a spoofed RA claiming to be the default router, diverting all traffic through their system, a form of a man-in-the-middle attack. The mitigation steps are like the RA guard. It configures switches to filter unauthorized RA messages. And the NDP inspection validates NDP messages against a trusted database of MAC and IPv6 address mappings. And the next is neighbor cache exhaustion, DOS attack. In this, attackers flood the network with fake NS messages, forcing devices to store bogus entries in their neighbor cache. This exhausts memory and prevents legitimate communication. The mitigation steps for such attack are like rate limiting. Restrict the number of NDP messages processed per second to reduce the impact of flooding. Dynamic cache management. Automatically remove stale or suspicious entries from the cache. Next is rogue router advertisements. In this, an attacker sends malicious RAs to misconfigure devices, such as assigning them an invalid prefix or redirecting them to a fake gateway. The mitigation steps are: secure neighbor discovery. Send enhances NDP by using cryptographic signatures to authenticate RA messages. Manual RA configuration. In sensitive environments, configure trusted routers manually and disable automatic RA processing. Another vulnerability is the lack of built-in authentication. The NDP messages lack native mechanisms to verify their authenticity, leaving them vulnerable to tampering. And the simple mitigation steps are implementing IPsec. Use IPsec to encrypt and authenticate NDP messages. And send, it provides a cryptographic framework for validating NDP communications. NDP is a powerful protocol that makes IPv6 networks more dynamic and efficient in handling key tasks like router discovery, prefix discovery, and address resolution. However, its vulnerabilities can be exploited if not properly secured. By implementing tools like RA-Guard, Send, and NDP inspection, network administrators can significantly enhance the security of IPv6 deployments. By understanding and securing NDP, you're one step closer to mastering IPv6 and ensuring robust, secure networks for the future. We will now discuss about the routing in IPv6, which is built upon the principles established in IPv4 while addressing its limitations. It leverages IPv6 enhanced design to simplify routing and ensure scalability, efficiency, and security. Let's explore the differences between IPv4 and IPv6 routing. Differences between IPv4 and IPv6 routing. While the fundamentals of routing, finding the best path between source and destination, remain the same, IPv6 introduces significant improvements such as expanded address space. IPv4 uses 32-bit addresses, leading to address exhaustion and complex workarounds like NAT. IPv6 employs 128-bit addresses, eliminating the need for NAT and enabling efficient routing across the Internet. What is the impact on routing? The IPv6 routing tables are more scalable as each device can have a globally unique address, reducing the complexity of managing private and public address translations. Simplified header processing. IPv4 includes optional fields in the main header, which can vary the size and increase processing overhead. While IPv6 uses a fixed 40-byte header with optional information moved to extension headers. The impact on routing. The routers can process IPv6 packets more efficiently, reducing latency and improving performance, especially for high-throughput networks. Fragmentation. In IPv4, routers are responsible for fragmenting packets that exceed the MTU. While in IPv6, end devices handle fragmentation, while routers only forward packets. The impact on routing is that it simplifies router responsibilities, freeing resources for core routing tasks. Built-in multicast and anycast. The IPv4, multicast and anycast are supported but not integral. While in IPv6, both are natively integrated, allowing more efficient routing for group communications, such as video streaming, online gaming. Route aggregation. IPv4 has limited aggregation capabilities, often result in large routing tables. While the IPv6 supports hierarchical addressing with prefix-based aggregation, significantly reducing the size of global routing tables. Let us now discuss about routing protocols supporting IPv6. Several protocols have been adapted or designed specifically for IPv6, ensuring compatibility and optimization for modern networks such as OSPF v3, which is open shortest path first for IPv6. It is an updated version of OSPF designed to support IPv6. It uses the same link state principles as OSPF v2 but separates address families for IPv4 and IPv6. The key features are: OSPF v3 uses link local addresses for communication between routers. It supports multiple address families, IPv4 and IPv6, simultaneously. It also enhances security by using IPv6's native authentication mechanisms. The use case may be the enterprise and large-scale networks that require efficient routing with rapid convergence. Next is RIPNG, which is Routing Information Protocol Next Generation. It is a simple distance vector protocol adapted for IPv6. RIPNG operates similarly to RIP in IPv4 but supports IPv6 specific features. The key features are like: it updates routes using hop count, with a maximum limit of 15 hops. It periodically sends updates to maintain routing tables. And uses UDP on port 521 for routing communication. The use case may be smaller networks or as a fallback protocol in less complex environments. Next is BGP, the Border Gateway Protocol for IPv6. BGP is the real protocol for exchanging routing information across autonomous systems in the Internet. The IPv6 version operates similarly to its IPv4 counterpart. The key features are that it handles large-scale routing with extensive policy control. And supports both IPv4 and IPv6 with separate routing tables. The use case are Internet service providers and organizations managing interdomain routing. Another protocol is ISIS, the Intermediate System to Intermediate System. It is a link-state protocol supporting both IPv4 and IPv6. ISIS does not depend on IP for routing updates, making it robust and versatile. The key features are that it uses a single database to manage IPv4 and IPv6 routes, and offers fast convergence and scalable operation. The use case are like backbone networks and service provider infrastructures. The next protocol is EIGRP for IPv6, the Enhanced Interior Gateway Routing Protocol. It is a Cisco proprietary protocol that extends EIGRP's capabilities to IPv6 networks. The key features are that it operates on IPv6 specific transport and uses link local addresses for routing updates, and supports both IPv4 and IPv6 independently. The use case is the Cisco-based enterprise networks. In summary, the IPv6 routing represents a leap forward from IPv4 by addressing scalability, efficiency, and performance bottlenecks. With protocols like OSPF v3 and RIPNG, networks can handle the demands of modern Internet applications. As IPv6 adoption continues to grow, understanding its routing principles and protocols is vital for building and securing robust networks. This outline ensures the foundational topics of IPv6 are comprehensively covered while incorporating ethical hacking perspectives. Let us now discuss about the techniques for transition. As the Internet moves from IPv4 to IPv6, transition mechanisms are essential to ensure smooth interoperability between the two protocols. The two widely used techniques are dual-stack implementation and tunneling mechanisms. The dual-stack implementation. It allows a network or device to operate with both IPv4 and IPv6 simultaneously. This approach enables seamless communication across both protocols during the transition period. So, how dual-stack works: in this the devices are configured with both IPv4 and IPv6 addresses. The device chooses the protocol to use based on the destination's address. If the destination supports IPv6, the device prioritizes IPv6. If IPv6 is unavailable, IPv4 is used as a fallback. The advantages of using dual-stack are like interoperability. It ensures devices can communicate with IPv4 only and IPv6 only networks without additional mechanisms. Incremental deployment. The organizations can gradually migrate to IPv6 without disrupting existing IPv4 services. End-to-end connectivity. It removes the need for translation mechanisms in mixed environments. While the disadvantages are like: it is resource-intensive. The devices and networks must maintain dual routing tables, which can increase memory and processing requirements. Increased attack surface. Running both protocols doubles the potential vulnerabilities and entry points for attackers. For example, a web server configured for dual stack will have two DNS records. For IPv4, a record -192.0.2.1. And for IPv6, Quad A record -2001 DB8.1. Clients will resolve the appropriate record based on their supported protocol. Another one is tunneling mechanisms. The tunneling encapsulates IPv6 packets within IPv4 packets to transport them over an IPv4 network. This is essential for connectivity when native IPv6 infrastructure is unavailable. The key tunneling mechanisms are 6-to-4. It automatically encapsulates IPv6 packets in IPv4 headers for transport between dual-stack networks. How it works. The 6-to-4 uses a reserved IPv4 address, 192.88.99.1, to identify and route encapsulated traffic. The IPv6 addresses starting with 2002:16 indicate 6-to-4 usage. The limitations are that it requires public IPv4 addresses, making it unsuitable for NAT environments. The performance can degrade due to reliance on relay routers. Next is Teredo. It enables IPv6 communication over NAT IPv4 networks by encapsulating IPv6 packets in UDP. How it works. The Teredo assigns a unique IPv6 address to each device behind a NAT. And the Teredo servers and relays manage tunneling and address resolution. The limitations are like: it is slower due to the overhead of encapsulation and relay processing. It is less secure as it introduces additional points of attack. The advantages of tunneling are: facilitates IPv6 connectivity without requiring immediate infrastructure upgrades. Allows IPv6 experimentation and deployment on existing IPv4 networks. And the disadvantages of tunneling are: the encapsulation adds latency. The security mechanisms, such as firewalls, may not inspect tunneled traffic, increasing risks. Let us now discuss about challenges in IPv6 adoption. Despite its advantages, IPv6 adoption has faced hurdles. Two key challenges are the compatibility issues and configuration pitfalls. Addressing compatibility issues. The IPv6 is not backward compatible with IPv4. Devices and networks must use transition mechanisms or dual-stack implementations to enable communication between the two. The specific issues are: legacy devices and applications. The older devices or software may not support IPv6, requiring significant upgrades or replacements. Network equipment. The routers, firewalls, and switches must be IPv6 capable to support native IPv6 traffic. To handle such situations, conduct a thorough inventory of devices and applications to identify compatibility gaps. Upgrade critical infrastructure to IPv6 capable hardware and software. Use dual stack and tunneling as temporary solutions during the transition. Next is the configuration pitfalls. The misconfigurations during IPv6 deployment can create security vulnerabilities and operational issues. For example, the inconsistent security policies. The IPv6 traffic bypasses firewalls and intrusion detection systems configured for IPv4. The complex addressing. The expanded address space in IPv6 increases the risk of errors in manual configurations. The insufficient training. The network administrators unfamiliar with IPv6 may inadvertently create misconfigurations. The solution to such problems is like: automate configurations. Use SLAAC or DHCPv6 to minimize manual errors in address assignment. Align security policies. Ensure firewalls, IDS/IPS, and other security tools are configured for both IPv4 and IPv6 traffic. Training and awareness. Provide IPv6 training for IT staff to ensure they understand the protocol's features and best practices. Thank you, everyone, for actively participating in today's session. Today, we've had a comprehensive discussion on IPv6 addressing, configuration, and transition techniques, covering the challenges IPv4 faces and how IPv6 addresses them. The IPv6 address configuration. Transition techniques. In our next lecture, we'll move into the routing basics. If you found this session helpful, please like, share, and subscribe to the channel to support more educational content like this. Don't forget to hit the bell icon so you're notified when the next lecture goes live. Thank you, and see you in the next session.